We're going to look at this problem. It says the jet plane is traveling with a constant speed of 110 meters per second along the curved path. Determine the magnitude of the acceleration of the plane at the instant it reaches point A. Now, point A is where y is equal to 0. Now, you can also see from the picture that at point A, x is equal to 80. Now, the equation for the curve is given there is 15 log of x over 80. So let's take a look at this problem. So we're going along this curved path, so we're going to need to calculate the radius of curvature at the point we're interested. The point we're interested is 80, x equal 80, y equals 0. And we have to calculate the radius of curvature, and that's calculated, it's usually represented by rho and calculated this way. So again, you can see we're going to need the first derivative and we need the second derivative. As I said, the equation for the curve is given. That's going to be 15 log of x over 80. And dy dx, again, it'll be the derivative of this. Remember, this is just a constant, so we can bring it forward here. Remember, the derivative of the log is 1 over whatever that argument is. Times the derivative of the argument. And so this is just like a constant of 1 over 80 times x. It's almost like a 2 times x or a 5 times x, except here we have 1 over 80 times x. So the derivative of that is just 1 over 80. And so that's going to give you 15 over x. And then we want to evaluate at the point A, and the point A had these coordinates. So we want to evaluate this at x equals 80. So the derivative of the point we're interested in is going to be 15 over 80. Now let's take the second derivative. And so we want the derivative of this. Now this is the same as 15 times x to the minus 1. So when we take the derivative, we'll bring the minus 1 forward. And subtract 1 from the exponent. So it's going to be minus 15 over x squared. And we'll evaluate that at x equal 80. And so that's just going to be minus 15 over 80 squared. And when I put that in my calculator, I got 0.0023. And so let's find the radius of curvatures given up here. So let's go ahead and put our values in. It says 1 plus 15 over 80 squared to the 3/2. And then the second derivative, put that in over here. 3, like that. So again, first derivative squared to the 3/2 divided by the second derivative. And there should have been a negative over here, by the way. I forgot that negative. Of course, it's going to go away since we're taking the absolute value here. So we can actually ignore the negative. And when you put this in your calculator, I got 457.9 meters. Now it's asking for the acceleration, excuse me. And now the acceleration, now the tangential acceleration is 0 because we had a constant speed. It says it was traveling at constant speed, so a tangential is 0. Now, but since it's going around the curve, it's going to have a normal acceleration. And you remember that's always the velocity squared divided by rho. And the rho is what we just calculated here. And we were given that the velocity was 110 meters per second. And we're going to square that, divide by 457.9 meters. And that's going to be 26.42 meters per second squared. Again, anytime you're going around a curve, if a curve's involved, you may or may not have a tangential acceleration. That'll have to be given to you, but you will always have a normal acceleration anytime your velocity is not 0. In other words, if you're moving, you'll have this normal acceleration. And so if you're given, if it's a circle, you might just know the radius. But if it's an arbitrary curve, you're going to have to use this equation. The equation was given up here to calculate the radius of curvature. Now we're going to take a look at this problem. It says the box of negligible size is sliding down along a curved path defined by the parabola 0.4 squared. When is it point A? And at point A, x is 2 and y is 1.6. The speed is 8 meters per second. And the increase in speed is 4 meters per second squared. Determine the magnitude acceleration of the box at this instant. Now, of course, the increase in speed, the dv dt, that's just the acceleration. So let's take a look at this problem. So we're given the point at which we want to calculate the acceleration, and that's the point x equal 2, y 1.2. Again, we're going along a curved path, and so we're going to need our radius of curvature equation, which is this right here. And now we're given that the velocity is 8 meters per second. And the dv dt is 4 meters per second. That's going to be our acceleration. And so this is like our tangential velocity and our tangential acceleration. Kind of think of those 4 meters per second squared. And we're also given the equation for the path. So we're going to use that to find out our dv, dx, excuse me, dy, dx, and the second derivative with respect to x here. So let's write this down. Y is equal to 0.4 x squared. So we're going to be working with that. And we're going to need the derivatives. So dy dx, it's going to be 0.8 x to the first power. And let's go evaluate that at x equal 2. And that's 0.8 times 2. And that's going to be 1.6. And then the second derivative is just going to be 0.8. Now, we really don't need to do any more because it's going to be 0.8 no matter what. So if it's evaluated x equal 2, or no matter where, it's going to be 0.8. So now we can substitute everything into our radius of curvature. Again, keep this equation in mind right here. 1 plus 1.6 squared to the 3/2 divided by the absolute value of the second derivative, which is just 0.8. Put that in your calculator, and it comes out to 8.39 meters. That's our radius of curvature. And then we'll find the acceleration. Again, the tangential acceleration is given. And we're going to have to find the normal acceleration. Remember, that's always the tangential velocity squared divided by the radius of curvature. And tangential velocity was given as 8 divided by 8.39. And that is 7.62 meters per second squared is the normal acceleration. And then our acceleration will be the magnitude of the tangential and normal, which is going to be, again, tangential is 4 squared. The normal 7.62 squared. And this is going to be 8.61 meters per second squared. Again, anytime you're going around a curve, you're going to have this normal acceleration. So you'll have to use this equation up here always to calculate. Not unless you're going around the circle. If you're going around the circle, this is just going to be the radius of the circle. Or sometimes the actual radius of the point you're interested in will be given to you in the problem, in which case you don't have to calculate this at all.